Do you know that there is no active steering system on a train? Then, how train wheels follow a curved track? Let's find out in this video. It will be easy to understand with 3D animation. This is a train coach and 2 bogies. Coach is fitted on the bogie frames. Wheel sets are connected with bogie using bearing. Thus, train weight is supported by the wheels. We already mentioned before that wheel set is actually 2 side-by-side wheels joined with center axle. It always rotates as a single unit. That means one side wheel cannot rotate faster than the wheel on the opposite side. Bearing on both ends helps it to rotate quite freely while supporting the total weight on the wheels. A rail wheel set can follow a curved rail without any external steering force. The secret is in its design. You probably know that rail wheel's outer surface is not completely cylindrical. If it was, then wheel set could be able to follow straight rail lines, like a car wheel rolls on road. But when the rail's curved section begins, there will be no steering force to turn the wheel set to follow the curved rail. This means a cylindrical shape cannot follow a curved rail track. That's why rail wheels are not cylindrical in shape. Rail wheel's outer thread section is slightly semi-conical. This is a cone, and this is a semicone. On a plane surface, a semicone cannot roll straight. You can clearly see here. At green color marked side, circumferential length of the circular section is smaller. Opposite side marked with violet, this side circumferential length is larger. Or you can say green side diameter is smaller and the opposite side diameter is bigger. At same rolling speed, larger section will try to cover more distance than the smaller side. While rolling, a semicone always turn towards smaller side. A rail wheel set follow the same physics principle. Let's assume this wheel set running on this rail track. Thread section of wheels, which is in contact with rails, are marked with red color for better understanding later. Both sides the running thread diameter are same. That means this wheel set will act like a cylinder and will keep rolling straight over the rail track. Did you ever notice a rail track carefully? Rails are not installed vertically straight. Rails are slightly tilted inside. This track design increases contact surface between rail and wheel, which in turn provides better traction for the wheels and helps to reduce wear and tear at contact points. Normally, a wheel set seats on a rail track like as it's shown here. Semi-conical shape of the wheel thread section and this rail track design also provides an important characteristics. When an object is at rest position on a slope, reaction force will be perpendicular to the contact surface. These are the 2 components of that reaction force. If this angle is theta, then vertical force component is r cos theta. And the horizontal component is r sin theta. If this slope angle changes, the theta value will change too. If angle increases, the r sin theta value will increase too. Conversely, if angle is reduced, then r sin theta value will decrease. Similarly, at rail and wheel contact points, reaction forces will be inward. We can divide it into 2 components. One is horizontal component. Other one is vertical component. While rolling straight, if wheel set shifts a little bit on the left side, then wheel reaction force direction will change due to changes in contact slope. Now, horizontal reaction component on left side wheel will increase and, on the right wheel, it will decrease. So, net horizontal force will be acting towards right. This force will help to shift the wheel back to normal position. In opposite, if wheel set slightly moves to the right side, then horizontal reaction force on the right side wheel will increase. This extra force will push wheel set back to normal position while rolling on the rails. This way a wheel set adjusts its position while rolling on the tracks. If wheel set moves beyond the tolerable limit, then it would fall off the track rails. That is why wheel flange sections are added as a last resort to prevent wheel derailment from the track. As you can see, when a straight rail track starts turning to the right side, primarily a rolling wheel set will try to go straight. This will shift the wheel set slightly left side on the track. As a result, the contact point between the wheel and rail on both sides will change. Right wheel's running thread diameter will be smaller, and left wheel's running thread section's diameter will be larger. Now wheel set will act like a semicone. We know that while rolling, a semicone turns towards smaller diameter side. This will provide steering force to the wheel set to run on the curved rail. And wheel set keep rolling on the curved rail easily. During this, net horizontal force will be acting against centrifugal force. When straight rail section arrives, this net force will help to shift the wheel set back to normal position on the track. If both wheels are fitted opposite way, then reaction force direction would be outward. At the starting of the curved rail, semi-conical shape is in opposite way, its smaller section is at wrong side. This wheel set will try to turn in wrong side instead of following curved rail. That's why rail wheels are not designed like this. If you found it interesting, then give it a like. Thank you for watching.